Hi everyone. Thank you guys for attending and for being here, especially the viewers via the YouTube channel. Today we have our new presenter, Sidanth, who will be presenting on the application of operations research methods and fundamental graph theory algorithms for the creation of IS networks. And basically, he'll be touching on the introduction to the algorithms which he has applied in his research, and as well as discussing some of his key findings. Sid, I've had the pleasure of studying with him throughout the degree, and now we're part of the same master's group, so I'm looking forward to what you present. So without any further ado, over to you, Sid.
Thanks, Sidanth, for the introduction. Professor, I think maybe just share screen. Okay, so good afternoon, everyone. As the chair has said, my name is Sidanth. I'm a master's student under Professor Rautal. My research is focused on the application of fundamental graph theory algorithms and operations research methods for the creation of industrial symbiosis networks. With the current situation we find ourselves in, it is imperative that we find solutions that remedy the current economic climate and improve and preserve our environment. And I believe the solution is industrial symbiosis. So what is industrial symbiosis? Industrial symbiosis, or IS, is a viable approach for improving a company's operational and environmental performance by allowing industries to exchange material and energy flow as a collective approach to competitive advantage. It also allows for a systematic approach to sustainability. The idea of industrial relationships mimicking organic relationships found in nature was put forth by George Renner in 1947. So this concept is not new. And in fact, the IS in Kallenberg, or the industrial symbiosis in Kallenberg, is the go-to example where a group of companies in Denmark, they decided to exchange in resources due to the low availability of groundwater. And it has since allowed for the realization of low environmental impact and improved economic performance. So we can talk about the need for industrial symbiosis. Due to the stringent environmental regulations imposed on industries as a response to negative environmental impacts the industrial activity has had on the environment, as well as the depletion of our non-renewable fuel sources, it has become increasingly difficult for industries to ignore inter-industrial collaboration. And industrial symbiosis, it presents itself as a viable solution to reconcile the economic, social, and environmental concerns surrounding industrial activity. So by engaging in industrial symbiosis, companies, they can stand to gain economic benefits, but without having significant environmental impact. Industrial symbiosis, it also promotes resource efficiency by allowing companies to exchange byproduct streams. Waste disposal costs and environmental impact can also be reduced by engaging industrial symbiosis. But when we're talking about industrial symbiosis, we're talking about matchings between suppliers and consumers. There are matching algorithms that are useful tools for identifying suppliers and consumers and creating pairings between them. Of specific interest is bipartite matching algorithms. So bipartite matching algorithms are those algorithms that create relationships between two disjoint sets of entities, U and V. Some examples are the Gale-Shapley algorithm. I believe Delencia gave a seminar on that 2 weeks ago. The Hungarian method, the Blossom's algorithm, the Edmonds-Karp algorithm. So these algorithms, they operate on problems that can be represented as a bipartite graph and seek to find best matchings, the best matching between two sets of entities. So to understand the rest of the presentation, it's important to first outline some basic graph theory algorithms. Graph theory concepts. So graph theory is a study of graphs. A graph is a mathematical structure used to model pairwise relationships between objects. A graph consists of a set of points or vertices and a set of edges that connects those points. Graphs can also have directed edges or arcs, like the graph that is shown on the right. And you can also have undirected edges in which there is no restriction on the flow of information or the direction of flow of information. As you can see, these graphs, they have cycles. And for ease of explanation, a cycle is defined as vertices connected in a closed chain, as you can see in here, for instance. So just to define a few graph theory terms, a path is a sequence of distinct edges joining a sequence of distinct vertices. A tree is a graph that contains no cycles, and there exists a path between any two vertices. So these are examples of trees shown to the left and right. And also a path and a cycle are not the same. And a tree is also a graph without any cycles. A bipartite graph is one in which the graph vertices are made up of two disjoint sets of elements, V1 and V2. And there's an edge, and the edge set E is the connections that pair the vertices from V1 to V2. Adjacent vertices are those vertices that are connected by an edge. And so with that definition, we can say that there are no adjacent vertices in V1 or adjacent vertices in V2. However, vertices are adjacent between V1 and V2, as you can see here. So with this introduction to graph theory out of the way, we can now transition to the main aim of the study. The IS problem formulation can be stated as follows. Given a set of M suppliers and N consumers, create an industrial symbiosis network that achieves maximum resource distribution and is feasible with respect to transportation costs and minimizes unshared byproduct material. And it is assumed that the following company data is available. So their geographical location, the byproduct requirements. So if they're a supplier, they have a supply of the byproducts. If they're a consumer, they have a demand. The unit price of the byproducts that they are proposing, either they are selling or they are willing to buy at that price per unit. And for instances where the percentage purity is important, we can imagine a consumer or a supplier makes that information available. The data can also be represented in this way. Suppliers are represented as blue dots and the consumers are represented as red dots. In green, you have the amount of resource that is for each company. So they are negative for the consumers. Negative values are allocated to reflect that a demand is required. And the geographical location of each company is represented by Cartesian coordinates. And in magenta, you have the percentage purity of the byproduct resource. There are 6 suppliers here and 6 consumers, and we can call this a 6x6 system. These data parameters are useful in determining which supplier should match with which consumer. For the graph representation of this problem, we can consider a graph G as an M by N system where there are M suppliers and N consumers. And the set of vertices are the suppliers and the consumers. And the edges are all the possible matchings between those two sets of vertices. The data parameters can be used to compute the strength of a supplier and consumer pairing. The question then becomes, what is a set of pairings or a matching M that leads to the minimization of unshared byproduct material and in a way where the total transportation cost is minimized? So to compactly represent these pairings, a matrix can store numerical values of these connections. We can define an assignment matrix. The assignment matrix stores pairwise relations between two sets of companies. In practice, the matrix is generated using 2 times D lists, where D is the number of parameters that are used to reflect the strength of the pairings. And there are 2 sets of them because they are one for suppliers and one for consumers. So note, so for example, if you look at the assignment matrix you see here, it's equal to some function of the data parameters for supplier I and J. For example, let's say if we only considered the resource capacity to weight the edges, maybe because we want to find a matching where the minimization of unshared byproduct is the constraint, then D would be equal to 1. And we have two such lists, one for the supply and consumer. And in this way, we can then generate or compute your assignment matrix. Note that the order in which the elements are in their respective lists affects the ordering of the row and columns in the assignment matrix. So the question now becomes, or these are the questions that we can pose. How do we pair companies together? Is there an optimal assignment of suppliers to consumers? Is it possible to achieve a byproduct distribution in which the amount of byproduct material ending up as waste is minimized? And how can industrial symbiosis be achieved without resulting in significant transportation costs and greenhouse gas emissions to achieve these resource exchanges? These questions seek solutions to problems that are analogs of well-established operation research problems. Operations research, or OR, is a well-established field and is essentially concerned with the management of organizations by scientific methods. So these are the 3 problems in OR that are relevant to industrial symbiosis: the optimal assignment problem, the network flow problem, and the transportation problem. So as the name suggests, the optimal assignment problem seeks to find out how best to assign a set of entities, one set of entities to another disjoint set of entities. And a common example is assigning n employees to n jobs, in which an employee, assigning an employee to a job incurs a cost to the company. And the objective is to create an optimal assignment or matching in which the total cost to the total cost of assignment to the company is minimized. For the case of the network flow problems, a common example is trying to find the maximal flow of commodity in a road network, where a road network is a very good example of a network graph or a flow graph. So a flow graph is a graph that is made up of directed edges, and you have a source and you have a sink node. And the objective is that you want to push, and each edge or directed each directed edge or arc has a flow value and a capacity. And the capacity is basically the weight of that edge, and the flow is the amount of commodity that is pushed through that edge. And the objective is to find a path from the source to the sink in which maximum amount of flow can be pushed through. So, for example, in a road network, you have roads of, you have many lanes, and of course, there's only so many cars you can or vehicles that the road can accommodate. And if we can think that a vehicle has a certain amount of goods, and there are many paths from or roads from a specific source to a destination, then what is the optimal route from the source to the destination such that you can send as much of this commodity as possible? The transportation problem, this is concerned with minimizing the cost of distribution of a product from a number of sources or suppliers to a number of sinks or consumers, such that the supply at each source is diminished and the demand at each sink is met. So from these research fields, 3 well-established algorithms were found: the Simplex method, the Hungarian method, and the Edmonds-Karp algorithm. I will now attempt to quickly give a conceptual understanding of how these algorithms work. Bear with me because, this can get a bit messy. So the Simplex method is a linear programming tool to find the optimal solution of a linear program. A linear program is a problem defined by a linear objective function subject to linear constraints. So for the transportation problem, you have Z being the objective function value, and you have an edge xij, and that is a pairing between a supply and consumer. Kij is the weight of that edge, or that is a function of the transportation costs. And we would want to find the set of edge connections between the suppliers and consumers such that the total transportation cost is minimized. And so just quickly to talk about these constraints, the first functional constraint you see here is the total amount of commodity that is sent from a supplier to all the consumers, j equals 0 to n, must be less than the total its total supply, and the total amount of commodity going to a consumer must be greater than or equal to its demand. So the way to understand how the Simplex method works, we can consider a simple example shown here. The Simplex method starts off by first requiring an initial solution. And the objective of the Simplex method is to output the optimal solution to the linear program. So in many cases, the initial solution is when the objective function value is 0, corresponding to the origin in most cases. For the case of industrial symbiosis, this could be where there are no pairings. So all xij is, or pairings that are made are all initially, there are no pairings. And so the objective function value is 0. And the Simplex method basically visits a sequence of points in the geographical space until it reaches the optimal solution. And so in this region that you see here, this blue region with its boundaries, these are, this represents the feasible region. And these are points that all satisfy the constraints of the problem. However, they may not be optimal with respect to the objective function. It may not be the minimum value of Z. And so the Simplex method, it makes use of the Simplex algorithm. So the Simplex algorithm is basically a tool that the Simplex method uses to determine in which direction it should move to get to the optimal solution. So the Simplex method, firstly, it always operates on the borders of the feasible region. So remember, the feasible region are defined by the functional constraints. Once you have the feasible region, the simplex method moves along the boundaries of the feasible region. And as you can see here, well, there are only two variables, x and y. And so there are two ways to get to the optimal solution. You either go along the vertical boundary or the horizontal boundary. And the choice in which direction you go depends on which direction corresponds to the largest increase in your objective function value, which in this case would be minus z. And obviously this corresponds to the minimum, the largest extent to which z is minimized. And so the simplex method, the simplex algorithm would move along the direction that sees this, the largest decrease in the objective function value. And it is implemented iteratively until the optimal solution is reached. Now, with all linear programs, it is known that the local minimums are all global minimums, and any local maximums are global maximums. So you are always guaranteed to reach the optimal solution. So the Hungarian method is an algorithm for finding the optimal assignment between the two sets of entities. I hope I haven't lost anyone. For the case of employees to jobs, consider this assignment matrix you have here. So each row corresponds to a unique employee, and each column corresponds to a unique job. And for example, E0 corresponds to the cost of assigning employee 0 to job 0. And so the Hungarian method will find the optimal assignment such that the total cost of assignment is minimized. In the case of industrial symbiosis, each each row corresponds to a unique supplier, and each column corresponds to a unique consumer. And when the Hungarian method is called, it will present a matching such as this. So what you see here is a bijection, and a bijection is basically the relationships that are made between two sets of disjoint data, such that there is exactly one edge that connects a vertex from the first set to a vertex of the other sets. And obviously this makes sense because you cannot have more than one employee for the same position in a company. Say there are only 5 positions available. And so when a matching or a pair, an assignment is made, in the case of industrial symbiosis, you are going to have the total supply being reduced and the total demand as well being reduced. But there may be a case where, given a matching that has been made, that where it's a bijection, you still have some supply that's greater than 0 for some suppliers, and you still have some demand that companies require. And so in that case, the Hungarian method would have to be called iteratively until the total supply or demand is met. And so just to explain this in terms of the linear program, it's required to minimize the objective function, where the values for these variables are restricted to 0 and 1. So this is a binary linear program, and the constraints are such that you can only have one edge connecting a vertex from one set to a vertex of another set. So with regards to the Edmonds-Karp algorithm, the objective is to maximize the amount of flow of some commodity from source to sink, such that the constraints are met. So let's look at this figure here. you have edges, and these edges have a capacity or they have their weights. And so initially in a flow network, this is a flow network, you have zero flow through the, for each edge. And for the first constraint states that for a given vertex, the flow coming into it must equal to the total flow going out of it. And all flows for an edge cannot exceed its capacity. So the maximum flow along this edge 0, 1 can be a maximum of 8. Essentially, paths from source to sink are determined that are biased to maximum flow from the source to the sink. So when a path is chosen by the Edmonds-Karp algorithm, the flow along the edges along the path, their flow values get updated. And when this occurs, the flow approaches its capacity value. The algorithm terminates when there are no paths from source to sink. And when does this happen? So say, for example, this flow is chosen. The flow will be chosen such that the minimum allowable flow can be pushed through this path. So the path 0, 1, 4, 6, that minimum flow is 7. By pushing that flow through it, you see that this edge 1, 4 can no longer be included in subsequent paths because it is said to be saturated. So when an edge is where the flow of an edge is equal to its capacity, it is said to be saturated. And the algorithm terminates when there are no, when all the edges incident to the source are saturated, or all edges that are incident to the sink are saturated. And the way paths are chosen is using the breadth first search algorithm, which the Edmonds-Karp algorithm uses. And for the case of industrial symbiosis, well, you don't just have one source and one sink. We have many suppliers and many consumers. And so the graph representation is a bit different. So you still have to have one source and one sink. So we have something called a super source and super sink. And you have one row of suppliers and one row of consumers. And the edges are computed accordingly. And pairings, the matchings between a supplier and consumer are reflected by which edge gets saturated between this set of vertices and this set of vertices. And the algorithm terminates when either all of these edges are saturated or all of these edges are saturated. When this edge is saturated here, which means the flow is equal to its capacity, the amount of supply this supplier has is diminished, it's 0. And so when all of the edges over here are saturated, it can then be said that all suppliers have no more supply. And in that case, your industrial symbiosis network is rendered. So just hopefully that was as detailed or understandable as I could have made it. I've applied these algorithms in my research already. Here's an example just to demonstrate the applicability. This is a simple 6x6 system shown previously, and the edge weights are weighted by the distance parameter, the capacity, and the unit price. And obviously the edges are weighted by some function. And so I left it as some function of the data parameters because the Hungarian method will make us matchings where the minimum cost is in which the pairing results in the minimum cost. However, for something like the Simplex method, a pairing is made in which you get the maximum increase in your or decrease in your objective function value. And that corresponds to a large objective function coefficient, Kij. So this function is algorithm specific. In any case, the company data for the suppliers and consumers are given. You compute the assignment matrix. And the Simon matrix has to be square, so there is some pre-processing required. I think I didn't explain what a spanning tree was, but in any case, not to go into a minimum spanning tree, but I use the minimum spanning tree algorithm to create a road network of sorts. So when I do compute relative distances between suppliers and consumers, it's not just equal to the Euclidean distance between the vertices. So it gives it a little bit more of complexity. And so the system was processed by each algorithm, and each algorithm produced an IS network. And the one thing that's common between all of them is that all the IS networks were feasible with respect to the minimization of unshared byproduct material, which had a value equal to the difference between the supply and the demand. And in this case, for all the networks rendered, the leftover unshared byproduct material was 16, which is the difference between these two values. What differed was how the supply was distributed. As you can see, each algorithm rendered different IS networks, implying that there are multiple solutions to the problem. And that's why you have multiple IS networks. And then and this implies that there is some bias that these algorithms have on which IS network is rendered. I also want to determine if the input has any impact on which IS network is rendered. And so remember, I said that the ordering in the lists of the data the ordering of the elements in the data list affects the ordering of the rows and columns in the assignment matrix. So over here, what I did was I reversed the ordering of the rows. So the first row was put as the fifth row, and the second row was put as the fourth row, and so on. And so I process it with the Edmonds-Karp algorithm. And as you can see, you get different IS networks. And this implies that the ordering of the elements in each data parameter list affects the IS solution that is rendered. And so the differences in those structures of the IS networks can be analyzed by extracting features from the network. And graph metrics are useful in this regard and have been used in social network analysis. And so graph metrics, they can help us with conducting comparative analysis between the algorithms. So I just have an illustration here to illustrate the graph metrics used. So you have the vertices and you have vertex degrees. A vertex degree of 1 implies that there's one edge incident to that vertice, incidence to that vertex. So for vertex degree of 2, you have 2 edges connected to that vertex. The number of edges are basically the total number of edges in the graph. So if this is some graph G, you would have 7 edges. The number of graph components in this case would be 3. And graph components are basically subgraphs of the graph G. And the total edge distance is basically if each edge had a weight of or distance of 1, then you have a total edge distance of 7. By using graph metrics, I was able to find key characteristics associated with each of these algorithms. And it also allowed me to determine the suitability of these algorithms in rendering IS networks. However, I needed to investigate how these algorithms perform with larger systems. So what about a system that's an n by n system, where the number of suppliers and consumers are not equal and they're not 6. Maybe they are 30 and 5 or 50 and 30. So I had to create a framework in Python. I think everyone who has done engineering would know that we've been more familiar with MATLAB. And so going to Python, we have to know what packages and modules to use to get the same outcome like MATLAB. So I've been using NumPy and Pandas, and I've created my classes. I've created a class to generate random sets of data of varying size, and each company parameter is randomized within bounds. And then I have a graph metric class that extracts the metrics from each IS network that's rendered that will then be used for analysis. I created a class for each of the algorithms. And this shuffling routine, basically it reorders the elements in each of the data parameter lists just to see how biased the algorithms are for a specific IS network structure. And then I then integrate the classes. So the framework was developed and a methodology was created using the scientific method to evaluate the suitability of the algorithms on systems of varying size. And I'm now at the point of discussing my results, working my thesis chapters. It can be said that, I can say that the Hungarian method seems to be the superior algorithm compared to the Edmonds-Karp or the Simplex method in creating IS networks that are feasible with respect to transportation costs. And future work would include applying these algorithms to real-life case studies to determine if the results are consistent. And yeah, so that's the conclusion of my seminar, and I now hand over to the chair. Thanks.
Thank you, Sid. That was a great presentation, and I think it's interesting to see, ever since the whole COVID lockdown happened, how far you've transitioned and how much more you've done. I think it was quite interesting to see that as well. Okay, so I think now that the presentation is done, the first thing we'll do is we'll go into any questions. So if anyone does have any questions, you can use the raise hand feature, or if you're prof, just actually raise your hand. Okay, so Mishka, I see your hand was up first.
Yeah, Sid, can you just go back to your slide on Edmonds-Karp, please?
1 second.
Yeah. Can you tell me how you found, okay, see, when I was thinking about what you were saying in terms of matching your suppliers and consumers, previously for the other algorithms, you were saying that you're trying to match one supplier with one consumer. But the truth is that one company, let's just say Sasol, for example, might have two byproducts that they're going to supply to two completely different companies. So I think that's where Edmonds-Karp sort of caught my attention, and I realized that that's what you're considering here. And I wanted to ask, how did you determine the super source and the super sink? Because you mentioned that the second and third line are your suppliers and consumers, but what is that super source and super sink?
So the super source and super sink are basically dummy vertices, and it allows it allows for the Edmonds-Karp algorithm or the Ford-Fulkerson algorithm or any network flow algorithm to create matchings, because the one thing that's required with the Edmonds-Karp algorithm is you have to have one single source and one single sink. And so you have to transform the problem to a single source, single sink situation. So I created something called a super source, and basically the amount of resource this source has is equal to the total supply, and the amount of demand this sink has is equal to the total demand. And so in this way, we can still say we want to find the paths from the source to the sink that results in a maximum flow of this commodity. And when you do find these paths, essentially you will have paths in which these edges that are between these two sets of vertices, they are in those paths. So essentially you're creating matchings. So let's say, for example, if that first supplier SM is paired with CN, that would be the result if the path on the top, it is very hard to explain, but if the path from the super source to SM to CN to the super sink is the chosen path. When that's the chosen path, then you would have the edge between SM and CN being saturated, and that's a pairing. And so when this is done, when you have all edges incident to the super source being saturated, it means that the total supply is diminished, and that's only going to occur when you have a matching being made with the consumers. And in the end, it's these edges between the supplier vertices and the consumer vertices that really matter.
Yeah, because I was just confused because I wasn't sure if that's like some sort of one entity that's sending in sort of your product, but now I understand it's just like a hypothetical thing that adds all your consumers and your suppliers.
Yeah,
Thank you.
it's just a transformation. Yeah.
Thanks.
Thank you, Zamishka, for the question.
Sorry, Chair. I think there were two questions, and actually the first one was about how do you handle multiple chemical types. So it wasn't that he. Anyway, let's answer that.
Yeah. So I haven't really thought about the multiple types because the thing that I noticed in my study was this algorithm is very suitable when the edge weights are a function of the commodity itself. So it's not, you don't factor in distance, you don't, or distance constraints, for example. And when it's a function of the flow of the commodity itself, the flow constraints are maintained, the capacity conservation constraints are maintained. Now, when you do factor in transportation costs, the Edmonds-Karp algorithm is rendered ineffective. You really have to change the algorithm. And I did have to do that. In fact, when you create a matching, you have to recompute all the edges again. And that's just because it's a function not only of the commodity, it's a function of the pairing itself. In terms of multiple commodity, I can imagine that maybe it can be done. Let's say if you had two substances, but in that case, you could say, okay, C1, which is commodity 1, and C2, which is commodity 2. I would imagine creating a variable C3, which is the sum of C1 and C2, and then maybe applying it with the Edmonds-Karp algorithm. So you would have, you would get an IS network in which you push through the commodities in such a way that you maximize the flow of those commodities from source to sink. And obviously, the ratios would be determined by, okay, the supply has so much of this commodity, supply has so much of another commodity. You could even change it where it's not a function of commodity, it could be the price. So the unit price for each commodity multiplied by the number of units you have, then that could be equal to an edge capacity. And when and so in that case, you could determine, you will get a matching, and that matching may be feasible with respect to how much of a commodity should be sent, between a supply and consumer, and obviously there are going to be constraints like the capacity constraints. How much that can a supplier give? How much can a consumer afford? So yeah, with regards to multiple commodities, I think there are many ways to model that. However, it does work well for a single commodity.
If I can comment on this, I don't think you can combine them. I think you actually have to do separate graphs for each chemical type. And so you do, for each type, you do a different graph. And then you have to think about things like the vehicle capacity, and then combining, if you have, and you might do something like including some kind of cost reduction if you are using the same route and the same vehicle that could transport the same chemicals. So if you like, there's another layer to this. It's like an iterative thing. So currently you are talking about one chemical, right? So for multiple chemicals, maybe that's the subject of your PhD actually. But for multiple chemicals, in principle, the first answer is you needed another graph and another application of this to solve that. And then as a wraparound loop, you might have to combine the results of those two matching exercises.
Yeah, just to comment on that, on the first question that Mishka had. In fact, there is a class of problems that address multiple commodities, and there's a certain cost to moving some commodity, and it's called the vehicle routing problems. And in fact, they are different class of problems. In fact, most of them are NP hard, which means they require heuristics, meta heuristics to be solved. And this is an exact algorithm. So obviously, as the professor said, you would need to have different layers, to try and get some solution that's the meta heuristics used in vehicle routing problems, render.
Yeah, I guess I also misunderstood a little, because if you look at that blue point right at the top, when you had multiple lines coming out, I assume those were different commodities that you were sending to different consumers. I didn't realize it was the same commodity that you're sending to all these different places.
Yeah.
So are you taking
so this
one
is basically
byproduct and separating it?
No. So this is one. Yeah. So I think I probably didn't explain properly. It's one commodity, and this graph here represents all possible matchings. So obviously this would be the edge set, and the matching would be a subset of that edge set. So not all of the edges will be shown in the IS network.
Okay.
Thank you for the questions, Mishka. Prof. Sneaky Lee suggested a PhD there. That was interesting. Said you'll be looking forward to it. Isaac, your hand was up next after Mishka.
Yeah, so afternoon, everyone. So I guess you guys answered my question already, basically, because what I was going to ask about was exactly the multiple material streams. How would that work? Because I did, obviously the premise is that it's a linear, problem. And if you go back to, I think, slide 14, maybe, Sid, if you can just go back, let me just check. Sorry, no, I think one more. The one where further back, yeah. The one where you had, I think, your MATLAB grid. Yeah, so if you look at your MATLAB, yes, that's the one. So if you look at all the green values that you got here, so all of those represent the same commodity, just different supplies and demands from each producer and consumer. Now, what happens when that's hypothetically like a list or a matrix of different values, for different materials? And Prof, I think you answered that a little bit, and Sid as well. So I guess, yeah, I mean, I think that a lot of the methods, going forward, once you have like a matrix of these different materials to optimize for, I think that makes it like a much more difficult problem as well. And I guess you said the meta heuristic way is also something you'll have to think about. I was also just, thinking of, I think about it sort of in pipelines, and then not necessarily vehicles, but even if you had pipelines and you've got these different materials, maybe there's constraints, around what kind of pipelines or material or actual, units you'll need to transport these different materials. So I guess that just, you can add like layers and layers of complexity to it. So it's a very interesting problem. Just wanted to comment rather than, because you guys answered my question before I asked. Yeah.
Thank you, Isaac. Thanks for the input there. Prof, your hand is up. Go for it.
Okay. Can we come back to the slide you had up before, please? Yeah. So just to comment on something here, you see there are two possibilities for the graph on the right, and that could represent a graph of the companies. So the vertices could be the companies, or they could be locations in a network, and it's just your endpoints are the companies. So if you like, there's a two-dimensional graph here. If you can imagine, on the surface of the page, there's the matching among companies, but then sort of in the plane going into the page, you've also got this network, this road network. So there are two dimensions to the matching here. You have to match the companies first, or I don't know whether first, but you have to match the companies and you have to match the road network. Now, I think what you've done, Sid, is simplify the road, the transportation problem by generating the minimum spanning tree, because that then guarantees a particular route between one company and another, right? So
Yeah.
in fact, that's my first question.
Yeah, so I used the minimum, so because it generated all of the data, then you just have the data in space. And so there wasn't a road network. So even if it was arbitrary, I used, and I think because I didn't mention this in the seminar, I used Dijkstra's algorithm to compute relative distances between each supplier and consumer. So the distances that you do factor into the weights, the coefficients in the objective function, they will be the shortest paths between suppliers and consumers.
Okay, and it makes sense, right? It makes sense to do it that way. In a way, it gets rid of this complexity that there are all these other possibilities for connecting just two companies, never mind the questions of which companies to connect, but just any two companies. It simplifies that problem. But in a way, by solving that problem, you actually miss an opportunity to model some of the other problems that you raised. You mentioned, what about that there are other constraints involved that, things like the cost of the chemicals or the purity, and you had mentioned, can't remember exactly what it was now, but you had mentioned a couple of other ones that you weren't able to currently model. And you see and you can still handle it as a pre-processing step, in that if you include those issues in your calculation of the cost matrix, so your cost doesn't only have to be distance. Your cost can be, the profitability of the trip, things like that. So by generalizing your cost calculation of the connection matrix, and maybe we can call it that. One is about connection, and one, both are connection. One is about spatial connection, and one is about kind of business connection. So by generalizing it so that it's not only spatial, you can generalize it also in terms of these other dimensions. Then you might be able to incorporate more of the, you might get better optimality in terms of other variables as well. Have you thought about that kind of approach?
Yeah, so I think in my technical work, I considered, the geographical locations, as well as, the fairness of a pairing. So there was a unit price for the supplier and the consumer. So let's say a supplier is selling his byproduct at 5 Rand per unit, and you have two consumers, one is 4 Rand per unit and the other is 3 Rand per unit. Then which is the best pairing to make? Well, for the supplier, it would be the one who's wanting to pay 4 Rand per unit, right? But in terms of the fairness, you'd want the unit price allocations to be agreeable. So the supplier and the consumer, their unit price allocations are the same. And so when I was doing my technical work, that Kij, the coefficients in the objective function for the transportation problem, I made it a function of the distances and the unit prices. And so all pairings made were between companies that agree on a price in terms of the numerical value of the unit price and are geographically closer. So then obviously if I had to add in, let's say, purity, so obviously a consumer wouldn't want to buy something from a supplier who's selling a low purity product. Then you'd want the purity requirements, in most cases, you'd want the purity requirements to be, more similar. So find the absolute difference between those values and then factor that into the objective function constraints.
So I think that's a different scale of optimization, but we can talk further offline on that. We'll talk further offline on this. Sidanth, you're on mute.
Not bad, guys. Phil, your hands up.
we're running out of time. Just a quick question. That function, if you go down to, I think the third last slide, or okay, just go up one more. One more. Yes. Okay. Okay. Go down. Yes. I mean, between your edges, no? So you have between the edges, you have basically there's a weight, an edge weight. You can say there is a function, that function with respect to distance, capacity, unit price. I just wanted to ask, like how are you, choosing the specific function, as the variables, they have different units, distance, capacity, price. Is there certain criteria you're following for specifying?
Yeah, so currently, I think the first step was just to see that these algorithms work for a specific size of the system. It does create IS networks, and from there I had to alter some of the algorithms or modify them, and then I needed to investigate how the size of the system, what can they say about the suitability of the algorithms. But I understand the question in terms of how much weighting do you give certain parameters, so transportation and stuff like that. But I think initially it was just to see how, if these algorithms are suitable, and then it would be, okay, finding the best weighting such that, because they do have different units. Yeah, so that then would come down, I think that would be case specific studies. So for example, in the sugarcane industry, I think I mentioned this to one of my colleagues, the sugarcane, yeah, I think we're running out of time, but the sugarcane industry, I think they would not want to, spend large amounts of cash on transportation costs. If they're trying to, when, let's say, for example, bagasse is their byproduct, and bagasse could be used for producing diesel. Now, what's the point of traveling far distances to make a certain amount of diesel? It may not make sense. So the transportation cost would have a very large weighting for that.
Okay, thank you very much.
Okay, thanks Phil for the question. I think based on the time factor, guys, I think we just draw the technical questions to a close. Does anybody have any comments on the actual presentation and its contents?
Yes, I have a comment. It was very, I like the graphical elements. They really, they worked well with what you were describing. I think maybe it's a bias because, I worked in something similar with graphs and edges and so forth. The way it was it was well presented from that aspect that I could, understand it quicker and grasp the concept quicker. So that's that's what I liked about this presentation.
Thanks.
Okay, Prof, hands up.
Okay, so I thought the industrial symbiosis as a concept, you could have introduced that from earlier on. So I think in your first few slides, you hadn't explained about connecting and what it was actually going to do, because you mentioned what the effect was. You said industrial symbiosis will reduce consumption and so on. But it would have been nice before that to explain about the transfer of chemicals. You have it much later on after you did the graphs and so on. So you always want to establish the actual problem and the main approach earlier on. And then, but that was just the one thing that's easy to fix. Overall, I appreciated the time you took to establish the concepts in graph theory and all those things. So in a way, it's a nice build up to a longer series on this topic, because you haven't, of course, presented on the many results that you've been showing me. So I guess you're intending as a longer series there.
Yeah, I was a bit worried about the time, and rightly so. So I thought, okay, if I do get a chance to present again, that will be the main findings from my results.
Mm.
So, yeah.
Okay, great. Thanks, Sid.
Okay, so yeah, just I'm looking at the participants pop up. There's no further questions, no further comments. So I think with that, thank you, Sid, for the presentation. It was very beneficial to our group in the long term, and also we learned quite a bit about what you're doing now and what the future may hold for you and us as a group. I think with that, that would be it, and the seminar drawn to a close. Thank you.
Thanks, Sidanth. Thanks, everyone.